Kia ora tātou. Welcome to this section 2.11 on state machine programming. Now there's some similarities between this and finite state machines, and there's some differences. So you need to make sure that you have these two ideas separate in your head, but there are some comparable things that happen in both. Okay, so first of all, the reason we look at state charts when writing programs is that it's really difficult for new people to programming, novice programmers, people who haven't done a lot of it before, to actually build something more than a trivial program. If we want to write a program for a system, we need a good, strong methodology that can help us design some software, and which is robust enough for change, especially in a situation where we're wanting our system to be responsive and reactive to the real world. Now, often flowcharts are used to help students begin programming. I want to go over flowcharts, and the reason for that is that they're not as useful for reactive and responsive systems as a state machine diagram. So let's have a look at a flowchart here. I've got this flowchart for a production process, and I've chosen this one because it's sort of similar to a role I had when I worked in London, and in a company that manufactures things, and I worked for an aerospace manufacturer then. And what happened there is that the client would come along and say, hey, I want 25 of these display units for my 747, or I want, you know, some of these joysticks for my Eurofighter or something like that. And then they would write up their internal documentation for this purchase. And this traveler documentation is to do with the fact that it travels with the product as it goes through the whole factory to make sure that everyone knows who this is for, what its purchase order number is, who's going to look after it, where it's gone, and where to go next. Okay, so that's the traveler documentation. So the next thing that happens is after that documentation is written, is they check to see if the material is in stock. Well, yes, it's in stock. So then we check to make sure that the tooling is in stock. And what I mean by that is some of these pieces of equipment required quite technical and well-machined parts. They have to go inside aircraft. And so there are particular tools that are used. Do we have the right tooling to actually make this piece of equipment and mold it out of plastic or machine it out of metal? Okay, and yes, we've done it before, so we've got those. And then it goes in and it's actually made, okay? And then it comes to the inspection department. And this is my role. I used to run the inspection department for this company. And the role there was to make sure that the technicians were doing the checking of things thoroughly to make sure that they were following their procedures. And so this would then come to our test and inspection department, because it wasn't just an inspection, but also a test, often a functional test of a circuit. And if it was correct, then it would go out of our department for post-processing, which is really just finalizing the paperwork to make sure that everything has been done, and then it would be cleaned and packed and then shipped to the customer. Okay, so a flowchart is quite good for a system like this. Everyone knows what's supposed to happen, and it does work for some software systems as well. So I'm not saying it's bad for software. I'm just saying that for reactive and responsive systems, there is a better way. And I'll show you why this is not so good for reactive and responsive systems. So let's come in here. First of all, we've got our traveler documentation, and someone checks to make sure the material is in stock. Well, of course, we've got a yes or a no decision here. So if it's not, the material is not, then they order the material, and then it comes in and it would come to our inspection department. We would check those materials to make sure they're okay. For instance, every box of resistors that came into the company was opened, and someone would check the resistors. They would pull out some of the resistors on the band of resistors, and they would check that they were the right color code. Then they would actually test some of those resistors. There was a specific number that they had to test with a multimeter to check the resistance was fine. And of course, if it was fine, then it would just go through the process. Do we have this tooling? No, then we have to order the tooling. And when it's come in and again passed inspection in the inspection and test department, it would go on and be machined. So after it's been machined, if it failed inspection, then we would decide whether it could be reworked. And some of the rework we would do, the electronics rework, the technicians would look after, and then it would go back in and come through inspection again. But of course, if it couldn't be reworked, if there was something wrong with it, then it had to be rejected and scrapped, okay? And of course, now I want to talk about the sort of things that happen that are outside the system, because a full system has to be completely reactive and responsive to things that happen that are completely under no one's control. Okay, so take for instance, the material comes into the or the traveler comes along, and we check to see if the material is in stock, and if it's not in stock, we order it, and then when it comes in, it's passed inspection. Well, what if it never comes in? Who's going to check to see that it's actually not come in? How long are we going to wait for it to come in? What if the people that we normally get our material from say, well, actually, I can't supply it to you in 2 days. It's going to take 17 weeks, or it's no longer available. So this sort of flow chart is not completely reactive and responsive to everything that can happen. And if we want to change this, then the flow chart just becomes bigger and bigger and bigger, and actually becomes very difficult to modify. Here's another issue. What if we scrap the parts? Well, nothing else happens. If everything is made and then we scrap the parts, well, who retell? Well, we don't. We just throw them in a bin and leave it. No, something else has to happen here. So you see, this system is okay up to a point, but it requires a smart person to come along and actually decide, well, actually, this has stopped at this point, I need to do something. Or there is no material coming in, or the material is going to be late, or we can't make that tool, or it's not available anymore, okay? Or what happens if we don't have the right equipment? So it needs a smart person in a system like this. And so if we want a fully robotically computer controlled system, then a flow chart is not very easy to write and manage. So what we're going to do is have a look at state machines. And I want to use a little example of a state machine. I want you to think about a vehicle. It could be an autonomous vehicle on the road, okay? So it has 4 states. It has 0 velocity, okay? So this is a speed versus time velocity graph. It has 0 velocity. So at this point, its state A is stationary, okay? So this is the stationary state, okay? Now, the light turns green at this point in time, and the truck starts to accelerate away. So at this state, it is accelerating, okay? It's increasing speed, so it's now in this state, that's state B, okay? So now it gets to the speed limit, and it changes to a constant state, of constant speed state, okay? So that's its steady speed, it's got a constant velocity. And then as we get along the road, the truck will detect that there's a red light or an orange light come up, and then it will start decelerating and come to a stop. Okay, so it's decelerating. And of course, when it's stopped, it's back in the stationary state A again. So these are the 4 states of our truck at the moment. Okay, we're not going to go too complex with this. If you start imagining things, you can imagine that, first of all, the graph won't be nice straight lines like this. Okay, this acceleration won't be a constant acceleration. Okay, it will be a slightly different change. It'll be slow, and then it will be you can imagine that. But we're going to go with something really simple in this case. So let's have a look at a state diagram for this. So I'm just going to delete those. Okay, so here's our state diagram. What we've got here is that we have 4 states. That it is a stationary state, and you can see how I've named each one of these: ST underscore stationary, ST underscore accelerating, ST underscore constant underscore speed, state underscore decelerating. I've used capitals as well because they're going to be macros in our code. And we can just draw these little blocks, okay? So as we're stationary, we're waiting for the green light. So when we get the green light, it transitions to this and it starts accelerating. And then when it gets to constant speed, it transitions to this state, constant speed. And when it sees the red or orange light, it transitions to this state called decelerating. And when it's come to a stop, it transitions to the state stationary, okay? So there must be some way of monitoring the speed of the vehicle, monitoring the traffic lights, pressing the accelerator, pressing the brake, all that sort of thing, which we haven't included in this diagram at all. This is a very basic introduction to this. But what I want to point out here is that this could actually be done with a flow chart, these 4, because it's just from one to the next, to the next, to the next, and then back again. However, what if our system needed to be reactive and responsive to changes in the lights as it's driving along? So as you pull away from the lights, you transition to the accelerating state, you start accelerating, and then what happens if you notice that there's a red light ahead? Well, you have to transition to this state, but there's no path here, okay? So at the moment, what you have to do is you have to get up to a constant speed and then decelerate before you can actually become stationary at the next light. Well, that's totally unsatisfactory. You could be within, 30 meters of the orange light, and then you're still not up to full speed. So according to this system, you have to go to full speed. You can't do that. That's not good enough. What we need is we need to be able to transition from this state to here. And you can see that what I've done here is I've created that transition line. Okay, so now we can say, well, actually, if the light turns orange, then we can transition from our accelerating state. So coming along here, where at some point we notice that it is orange up here, and then what we do is we start decelerating like this. Okay, so we just go up and down again like this. So this we would go from the accelerating state to the decelerating state, and then back to the stationary state again. And the same would happen also if, for instance, you're accelerating, you're decelerating here because you've seen an orange or red light. But as you're decelerating, the light changes to green again. Well, at the moment, you would have to continue down to stationary before you could start accelerating. So we put in another transition here. And you can see this is very easy to modify and change. If we're decelerating, we don't have to become stationary before we can accelerate again. We can just transition towards accelerating. Of course, there's a lot of checks and balances in here that we have to do, and we're going to look at some of those in detail. So let's have a look at how easy it is to do. So I'm going back to this document, and I've got my assignment here, and this is what you've got is you've got a block diagram. I don't know what this is. I'm just using the state machine at the moment. But what I've got here is, there are my 4 states, okay? And you can see that my 4 states are represented by a while statement for each state. So while this state is in stationary, do what's ever in here. Well, the only thing that's here at the moment is a transition. So the moment you enter this state of stationary, you start going towards you immediately change state to accelerating. And then it comes down here and we'll go into, well, the accelerating state, okay? So now let's just look at this. What is state? Well, state is simply just a variable. So I've got state starts at state 1. Now that's not very good. What I need here is I need an initial state, okay? So what I need to do is draw an initial state in my diagram. I haven't got one, okay? So I need to know which is the initial state, and it is the state stationary. So at the moment I've got state 1, which is state constant speed, so that's no good. What I'm going to do is just put a shortcut in here and say, hey, this is the initial state, so it will be here. And you'll see on all the diagrams there's actually a little dot or a square box which feeds into the initial state. So state is just a variable, and each state itself is just a macro for a value. So state stationary is 0, state accelerating is 3, state constant speed in this case is 1, state decelerating in this case is 2. Okay, so all they are is just values. And of course, we don't use magic numbers in our code. What we use is we use macros. So initially, state is set to be the value state stationary, which is here. And what we can do is we can actually add transitions as we want them to be added to our state. Of course, at this point in time here, how does it know to do this transition or this transition? And there are conditions which are attached to these, which we have to put in, because of course, it makes no sense for this to appear like this. There must be some if statements in here to control when it changes to the new state. So let's have a look at what it actually looks like. This is a bit more comprehensive, and it's got some things in it which are good and some things in it which need to be changed. So let's have a think about this. I'm going to go back to my state, and I'm going to open a project. I've got a lot of these already saved. Where's my truck state? Truck state machine. Right. Okay, so here's this state machine. Oh, by the way, if you want to sometimes I allow you to open and close these diagrams. This runs in Flash, which is a bit of a pain when it comes to Chrome, a little bit of a pain when it's in Firefox. You have to activate it so that you can save your own code if you want to. So here we are, we're in the state stationary, okay? So we're in state stationary. I haven't got my initial state here, okay? I need an initial state. So let's have a look here at some of these features in this machine and go through them slowly. While you're stationary at the traffic lights, what are you doing? You're monitoring the traffic lights. What else would you be doing? Listening to the radio? Well, that really doesn't help us in terms of an autonomous vehicle, but it might help with a human vehicle. But actually, what else would you be doing? If you have a look at some of the other states, you might also be checking for hazards. So I could take this and I could go down here and I could add another function. I can just drag this down a little bit. Oops, we've got to add a function, add an action. There we go. And I'm just going to put that in there. So you would also be checking hazards while you're sitting there at the traffic lights, okay? Just to make sure that you don't drive into someone when the lights are green and or the lights have turned green. What else might you be doing? I think that's probably enough for the moment. So you're monitoring these hazards. Now, when the light is equivalent to green, well, actually, there's something else here as well. There must be no hazards, okay? So we must, we can double click on this. We can apply the accelerator, right? We can, light is green, and we could say no hazards. And I might actually make that a function, I suppose. Something like that, no hazards. So there's no hazards, okay? We've got no hazards, we can safely drive off. Oops, I'm not adding a new state. Machine. I just want to move this over a little, well, no, I want to move this over a little bit. There we go. So at this point, there are no hazards, the light is green, we remove the brake and apply the accelerator. So these are actions, okay? This is the condition, this is the transition, this is the condition that causes the transition. And before we go into the next state, these are the actions that we want to apply, because we only want to remove the brake when we're transitioning and we only want to apply the accelerator. So let's have a look at the actual code for this. So while we're in the state stationary, so let's find stationary, there we go. Here's the stationary state. I'm gonna make this a little bit easier to read, make this a little bit bigger. So here we are in the stationary state. So what's happening? While the variable state has the value state stationary, it doesn't matter what it is, it's just a macro. While it has this value, we want to monitor the traffic lights and check the hazards, okay? So these will actually be function calls ultimately. So we could call them function calls, okay? And we would have to write those functions, okay? Right. Now, if the light is green and there are no hazards, so no hazards would have to be some sort of variable. So if there's no hazards and the light is green, then we can change the state to accelerating. So that what that does is it changes the value in the state variable to another value. It's no longer this one. If this is 1, this might be 2. So this variable now has a different value in it, okay? But it will still continue to carry out what is in this if statement, okay? And of course, what it does is it removes the brake. So remove brake could probably be a function call as well. You know, so you can go through and tweak these things. But the idea is that this will help you design a system before you write the nuts and bolts of it, okay? And this is really critically important. And of course, then you want to apply the accelerator, which would be another function. So you can see what's going to happen here is that we initially had the value of the variable state was 1 value, and it was in here continuously doing this. When it checked and found that the light was green and there were no hazards, then what happened was it changed the value in the state variable, removed the brake, applied the accelerator. It comes out of the if statement. It comes back here to the while statement and finds that state has now changed. Okay, the value in the variable state has now changed. It is no longer this value, it is this value. And so it will exit this while loop and go and find the point in time where state equals state accelerating, which of course is not down here. It will come to the end of this loop, it will come back around, and it will go back into this while loop, and then it will find that here it is here. So it will now enter this while loop and stay in this while loop. So this is how a state machine works. This is one way of implementing a state machine. And of course, in this state, what's going to happen is it's going to check the front distance to make sure you're not getting too close to anyone. You're going to check your hazards. You're going to increase your speed. Well, actually, you might also do a bit of monitoring of your speed as well as increasing it. So maybe increase speed, and because checking front distance might require you to actually do something. Okay, so now we've got two exits to this state. So now we have to make sure that every possible way of exiting this state is covered. And so there are only two ways of exiting this state. It will continue to check the front distance, continue to check for hazards, and continue to increase speed until something changes. And what we've got here is the speed equals the speed limit, or the front distance is less than a safe distance. So what we want to do is make sure that as we're accelerating away, we're not going to accelerate into the vehicle in front of us. We want to maintain a safe distance from that vehicle. Okay, and what we do then is we adjust the accelerator and then go to a constant speed. So that's one way of exiting or transitioning out of this state. Another way of transitioning out of the state is if we see a red light and then we stop accelerating. Well, stop accelerating means removing your foot from the accelerator pedal and apply some braking until we come, and then we are now in the decelerating state. So we're now no longer accelerating, we are now decelerating. We have seen a red light, we've removed our foot from the pedal and started the accelerator pedal and started applying a bit of braking. And now we're continuing to check the front distance and we are reducing speed, okay? Now, this checking the front distance is quite important because we don't just want to stop at the red light, we want to stop in the queue. So the distance to the queue is less than our stop distance, then we've got to come to a stop. And we apply the park brake when we're in this. So you can see this is the way you would work with a state machine. If you're trying to do this with a flow chart, it's impossible because there's just so many reactive things that could take place. I've said to apply the park brake here, but in here I haven't said to remove, oh, I have actually, I've said to remove the brake. So, but there are some other things in here that need a little bit more working out. So this is how a state machine works. And this is how the code is automatically generated from the state machine in my simulation tool. It's a great way of designing software. It's a very, very powerful way of designing software. And one of the most significant advantages of designing this software using a state machine comes from the original inventor of the state machine, a guy named Harrell, H-A-R-E-L. And he was designing the landing gear for a jet fighter. And he had all this information up on the board, and a test pilot came through and saw what was up on the whiteboard and looked at it and said, well, no, it doesn't work like that. It works like this. And the software engineer, Harold, realized at that point in time that actually you can get your client involved in designing software when it's like this, because they can understand this very easily. They understand the system, how it's supposed to work and what it's supposed to do. Now, you don't want to do that with this sort of software. They won't follow this, but they will follow this. So that's an introduction to the state machine. Key things: states, transitions, conditions, and actions. Actions can be in states and actions can also be in the transition. And there's loads of these on the internet. So I'm going to stop at this time and I'm just going to go on in the next video. Cheers.